Hello friends, I welcome you to my course on ordinary and partial differential equations and applications. In this course, in this lecture we shall discuss linear systems of ordinary differential equations. One of the most important concepts of analysis is that of a system of n simultaneous first order differential equations in several variables. Such a system can be expressed as dx1 by dt equal to f1 t x1 x2 xn, dx2 by dt equal to f2 t x1 x2 xn, and so on. The nth equation is dxn by dt equal to fn t x1 x2 xn. Here t is the independent variables, x1 x2 xn are n dependent variables of the independent variable t. Our aim will be to solve the system of differential equations. So, x1 x2 xn are unknown functions of the single variable t. Systems of differential equations arise quite naturally in many scientific problems. A solution of system 1 is a set of n functions x1 t, x2 t and so on xn t, such that dxj by dt equal to fj t x1 t, x2 t, xn t. That means the n functions x1 t, x2 t and xn t satisfy the system of differential equations given by 1. Now, for example, let us consider x1 t equal to t and x2 t equal to t square. Then these two functions provide us a solution of the simultaneous first order differential equations dx1 by dt equal to 1 and dx2 by dt equal to 2x1. We can see we have a system of two differential equations of first order. So, here we can, if you take x1 t equal to t and x2 t equal to t square, we can show that these two functions satisfy this system of differential equations. How it follows? You can see x1 t equal to t implies dx1 by dt equal to 1, okay, and x2 t equal to t square gives you dx2 by dt equal to 2t. Now, t is equal to x1, so dx2 by dt equal to 2x1. Therefore, x1 t equal to t and x2 t equal to t square satisfy the system of differential equations of first order dx1 by dt equal to 1 and dx2 by dt equal to 2x1. So, they form a solution of this system of differential equations. Now, if we impose the initial condition on the functions x1 t, x2 t and so on xn t as x1 t naught equal to x1 naught, x2 t naught equal to x2 naught and so on xn t naught equal to xn naught, then the system 1 together with the initial conditions 1 dash, okay, is called a initial value problem. So, here you can see at t equal to t naught the value of x1 is x1 naught, at t equal to t naught the value of x2 is x2 naught and so on, the value of xn at t equal to t naught is xn naught. So, if we are given these conditions together with the system 1, then the system 1 is called is a initial value problem. A solution of this initial value problem is n functions x1 x1 t, x2 t, xn t which satisfy the system 1 and the initial conditions given by 1 dash. For example, let us consider x1 t equal to e to the power t and x2 t equal to 1 plus e to the power 2t by 2. Then it is a solution of the IVP. IVP means initial value problem, and the initial value problem here is dx1 by dt equal to x1, dx2 by dt equal to x1 square. The initial conditions are x1 at t equal to 0 is 1, x2 at t equal to 0 is 3 by 2. Now, we have to show that x1 t equal to e to the power t and x2 t equal to 1 plus e to the power 2t by 2 is a solution of this initial value problem. So, if you first we have to show that x1 t equal to e to the power t and x2 t equal to 1 plus e to the power 2t by 2 satisfy the system of differential equations, and then we have also to show that they satisfy the initial conditions x1 0 equal to 1, x2 0 equal to 3 by 2. Now, x1t equal to e to the power t implies dx1 by dt equal to e to the power t. E to power t is x1, so dx1 by dt equal to x1 is satisfied. x2t is 1 plus e to the power 2t by 2. When you differentiate this with respect to t, what you get is dx2 by dt equal to 2 times e to the power 2t by 2, that is e to the power 2t. So, dx2 by dt is equal to e to the power 2t, which is equal to e to the power t whole square, and so we can write that as x1 square. So, dx2 by dt is equal to x1 square. So, x1t equal to e to the power t and x2t equal to 1 plus e to the power 2t by 2 satisfy the differential equations of this system. And also you can see that x1 at t equal to 0 is equal to e to the power 0, which is equal to 1. So, x1 0 equal to 1 is satisfied, and x2 at t equal to 0 is 1 plus e to the power 0 by 2, which is equal to 1 plus half. So, we have 3 by 2. So, x2 at t equal to 0 is 3 by 2, and therefore, x1 t equal to e to power t and x2 t equal to 1 plus e to the power 2t by 2 satisfies this system of differential equations together with the given initial conditions, and therefore, they give us a solution of the initial value problem. Now, first order systems of differential equations also arise from higher order differential equations for a single variable by t. Every nth order differential equation for the single variable by to the power by n, and this is nth derivative of y with respect to t. By n we are representing by n represents dn by over dtn is equal to f t by y dash by n minus 1, that is n minus 1th derivative of y. So, it can be converted into a system of n first order differential equations for the variables x. Now, what we do is we will convert this nth order differential equation to a system of differential equations of first order. So, let us write x1 t equal to y, x2 t equal to dy by dt, and so on xn t equal to dn minus 1 by over dt n minus 1, that is n minus 1th derivative of y with respect to t. Then from here we can see that dx1 by dt will be equal to dy by dt, and dy by dt is x2. So, dx1 by dt is equal to x2, dx2 by dt will be d square by over dx square, but d square by over dx square is x3. So, dx2 by dt is equal to x3, and so on dxn minus 1, xn minus 1 t is the n minus 2th derivative of y with respect to t. So, dxn minus 1 t over dt will be equal to n minus 1th derivative of y, and therefore, it is equal to xn. And dxn by dt is, if you differentiate this with respect to t, then dxn by dt gives you nth derivative of y with respect to t. So, dxn by dt can be written for this nth derivative of y with respect to t, and we have f t by is x1, y dash is x2, and so on n minus 1th derivative of y is equal to xn. So, this is f t x1 x2 and so on xn, which is clearly a special. So, now you can see there are n equations. It is a system of n equations, first order n equations, dx1 by dt equal to x2, dx2 by dt equal to x3, dxn minus 1 by dt equal to xn, and that the nth equation is dxn by dt equal to f t x1 x2 xn. So, this is a special case of the system given by equations 1. Now, let us for example convert the differential equation a n t dn by over dtn plus a n minus 1 t dn minus 1 by over dtn minus 1 and so on a naught y equal to 0 into a system of n first order differential equations. Now, as we have said, we will put x1 t equal to y, x2 t equal to dy by dt, and xn t equal to n minus 1th derivative of y with respect to t. Then dx1 by dt is dy by dt, so dxn by dt is x2, dx2 by dt is x3, and dxn minus 1 over dt, dxn minus 1 over dt is equal to xn, because xn minus 1 is n minus 2th derivative of y with respect to t. So, when you differentiate xn minus 1 with respect to t, you get n minus 1th derivative of y with respect to t, which is assumed is xnt. So, dxn minus 1 over dt is equal to xn, and dxn by dt. Now, you can see dn by over dtn is dxn by dt. Okay. So, this is dxn by dt. What we do is we transpose all these terms to the other side and divide by ant, assuming that ant is not equal to 0 for any t. So, then dxn by dt will be minus 1 upon ant, and then an minus 1, this is xn, then an minus 2 into xn minus 1 and so on a naught, and by is x1. So, we get n equations of first order which are dx1 by dt equal to x2, dx2 by dt equal to x3 and so on, dxn minus 1 by dt equal to xn, and the nth equation is dxn by dt equal to minus 1 upon a and t. Inside the bracket we have a n minus 1 t into xn plus a n minus 2 t into xn minus 1 and so on a naught x1. So, this is the bracketed expression, or you can say the right hand side is a function of t and the n variables x1, x2, xn. So, this system is of the form 1. So, you can see that the nth order differential equation which is given to us has been converted into a system of n differential equations of first order. Now, let us take a initial value problem. We can see this is a third order differential equation, d cube by over dt cube plus dy by dt whole square plus 3y equal to e to the power t. The values of the dependent variable y at t equal to 0 is given as 1. The derivative of y with respect to t dy by dt at t equal to 0 is 0, and d square by over dt square at t equal to 0 is equal to 0. So, we have to convert this initial value problem into a system of differential equations. Now, again let us say x1 t equal to y, x2 t equal to dy by dt, and x3 t equal to d square by dt square. Okay. So, then d cube by over dt cube will be dx3 by dt. So, this is dx3 by dt, okay, and we can then, this is dx3 by dt, and these terms dy by dt whole square plus 3y, if you take to the other side, what you get, e to the power t minus dy by dt is equal to x2, okay. So, x2 square. So, e to the power t minus x2 square minus 3 into y is equal to x1. So, we get dx3 by dt equal to e to the power t minus x2 square minus 3x1. So, now you can see we have three equations. First equation is dx1 by dt is equal to x2, because dxn by dt is dy by dt and dy by dt is x2. So, dx1 by dt is equal to x2, and dx2 by dt is d square by over dt square, which is x3. So, dx2 by dt is equal to x3, and dx3 by dt we have just now seen, it is e to the power t minus x2 square minus 3x1. Now, by at 0 is given equal to 1. So, you can see x1 t is equal to y. So, at t equal to 0, y is equal to 1, therefore, x1 0 equal to 1. So, x1 0 equal to 1, at t equal to 0, dy by dt is equal to 0. So, x2 0 is equal to 0, and at t equal to 0, d square by dt square is equal to 0. So, x3 0 equal to 0. So, the initial value problem, okay, the given initial value problem is converted into a system of first order differential equations with the initial condition x1 0 equal to 1, x2 0 equal to 0, x3 0 equal to 0. Now, if each of the functions f1, f2, fn in the system 1, okay, if each of the functions f1, f2, fn in the system 1 is a linear function of the dependent variables x1, x2, xn, then the system of equations is called linear. Now, the most general linear system of n first order differential equations is of the form dx1 by dt equal to a11 t into x1 and so on a1 n t into xn plus g1 t, dx2 by dt equal to a21 t into x1 and so on a2n t into xn plus g2 t, and the nth equation is dxn by dt equal to an1 t into x1 and so on ann t into xn plus gn t. So, this is a most general system of n first order linear equations, a linear system it is. You can see the functions f1, f2, fn, these are functions of t x1 x2 xn. This is f1 t x1 x2 xn, this is f2 t x1 x2 xn, and this is fn t x1 x2 xn. In all these functions f1, f2, fn, x1, x2 and so on xn, they occur in the first degree and separately. Okay. So, it is a linear system. Now, if each of the n functions g1, g2, gn is identically 0, if it so happens that g1t, g2t and so on gnt are identically 0, then for every value of t, g1t, g2t and so on gnt is equal to 0 for every value of t, then we say that they are identically 0, then the system 2 is called a homogeneous linear system, otherwise we call it a non-homogeneous linear system. Now, let us consider the case where the coefficients aij do not depend on t. So, we are taking a particular case of the homogeneous system where the coefficients of x1, x2, xn, the coefficients of x1, x2, xn, that is a11 t and so on a1n t, a21 t and so on a2n t and so on an1 t, an2 t, ann t, they are just constants, they do not depend on t. So, then such a system is called a homogeneous linear system with constant coefficients. So, this is of the form dx1 by dt equal to a11 into x1 and so on a1n into xn, dx2 by dt equal to a21 into x1 and so on a2n into xn, and dxn by dt equal to an1 into x1 and so on ann into xn. Now, this system we are writing it by equation 3, this system given by 3 can be expressed in the concise form. Now, you can see if the number of equations are very large, if the n is very large, then it will be very cumbersome to write these equations. So, we can write them in a concise form using the vector notation. What we do is if we denote xt equal to x1t, x2t, xnt, this column vector, then this xt is called a vector valued function. And if you differentiate this xt with respect to t, then dx by dt is another vector valued function whose components are given by dx1 by dt, dx2 by dt and so on dxn by dt. So, therefore, you can see the left hand side, which is dx1 in the first equation dx1 by dt, in the second equation dx2 by dt, in the last equation dxn by dt, it can be put in the form of a vector notation which is x dot means dx by dt. So, dx by dt will contain is a column vector having n components dx1 by dt, dx2 by dt, dxn by dt. The right hand side of these n equations is a11 x1 and so on a1n xn, a21 x1 in plus and so on a2n xn, an1 x1 and so on ann into xn. It can be put in the form of a matrix A multiplied by the vector x, where the matrix A is a11, a12, a1n, a21, a22, a2n, an1, an2, ann multiplied by, so the vector x, that is x1, x2, xn. You can see if you multiply this matrix A by the vector x, x1, x2, xn, then the first row of Ax will be a11 x1 plus a12 x2 and so on a1n xn, and then the second row of the matrix Ax will be a21 x1, a22 x2 and so on a2n xn. The last row of the matrix Ax will be an1 x1, an2 x2 and so on ann xn. And so, the n equations given by this 3 can be put in the form of a vector equation dx by dt equal to Ax. Now, if x1t, x2t, xnt satisfy the initial conditions, that is at t equal to t naught, x1 is x1 naught, x2 is x2 naught and xn is xn naught, then xt satisfies the initial value problem, then we can write the system in the concise form x dot equal to dx by dt equal to Ax, x at t naught equal to x naught, okay, because xt is equal to xt is x1t, x2t, xnt. So, at t equal to t naught, x t naught will be x1 t naught, x2 t naught, xn t naught, and we have assumed that x1 t naught is x1 naught, x2 t naught is x2 naught, xn t naught is xn naught. So, x t naught is equal to x1 t naught, x2 t naught, xn t naught, that is x1 naught, x2 naught, xn naught, and that we can write as x naught. So, x t naught equal to x naught, where x naught is equal to x1 naught, x2 naught and so on xn naught. So, you can see that the initial value problem can be expressed in the concise form, which is x dot equal to Ax, where x at t naught is equal to x naught and x naught is this column vector. Now, let us consider, for example, the system of equations dx1 by dt equal to 3x1 minus 7x2 plus 9x3, dx2 by dt equal to 15x1 plus x2 minus x3 and dx3 by dt equal to 7x1 plus 6x3. Then again, if you take xt to be the vector valued function x1t, x2t, x3t, then x dot will be dx1 by dt, dx2 by dt, dx3 by dt. So, this left side can be represented by the vector valued function x dot, and the right hand side we have here the coefficient of x1, x2, x3 are 3, minus 7, 9. Here x1, x2, x3 have got coefficients 15, 0, 15, 1 and minus 1. Here x1 has coefficient 7, x2 has coefficient 0, x3 has coefficient 6. So, the matrix A, okay, will be 3 minus 7 9, first row of the matrix A will be 3 minus 7 9, second row will be 15 1 minus 1 and third row will be 7, which is the coefficient of x1, then coefficient of x2 is 0 and then coefficient of x3, which is 6, multiplied by the vector x. X is the vector x1, x2, x3. So, if you multiply this matrix A by the vector x1, x2, x3, you get these right hand side, and left hand side is this x dot, which is dx1 by dt, dx2 by dt, dx3 by dt. So, this system of 3 equations, this you can see this is a homogeneous system of linear differential equations of first order. This can be expressed in the concise form x dot equal to Ax, where A is this 3 by 3 matrix. Let us now take up another problem. Here we are taking initial value problem. So, we have 3 equations dx1 by dt equal to x1 minus x2 plus x3, dx2 by dt equal to 3x2 minus x3, dx3 by dt equal to x1 plus 7x3. We are given that at t equal to 0 x1 is 1, at t equal to 0 x2 is 0, at t equal to 0 x3 is minus 1. Now, as in the previous example, here also if you take xt to be the vector valued function having components x1t, x2t, x3t, then the left hand side of this this system of equations is x dot t, because x dot t is dx1 by dt, dx2 by dt, dx3 by dt. So, x dot t and the coefficient matrix here, the matrix of the unknown functions x1, x2, x3 is 1 minus 1 1, okay, 1 minus 1 1, then here 0 3 minus 1, because the coefficient of x1 is 0. So, 0 into 0 then 3 then minus 1, and here we get the 1 then 0 then 7, the coefficient of x2 is 0 here. So, 1 0 7 and then the vector x, that is which has got components x1, x2, x3. Now, let us account for these initial conditions. So, xt is equal to x1, x2, x3. So, x0 is x1 0, which is 1, x2 0, which is 0, and then x3 0, which is minus 1. So, we have seen in this lecture how to write a linear system first order differential equations which is homogeneous in the concise form. Also we have seen how we can write a initial value problem where we are given a system of first order differential equations homogeneous system with the initial conditions in the concise form. So, by using the vector notation we can write the equations in a concise form. Now, in our next lecture we shall see how we can solve a system of homogeneous linear differential equations with constant coefficients. Thank you very much for your attention.